The cosmos holds secrets that shatter our understanding of reality. You are about to embark on a journey through 30 cosmic enigmas where the universe itself seems to break its own rules. By the end, you will possess a new perspective on the fundamental laws that govern everything. We will confront signals from the void that hint at intelligence and forces that tear at the fabric of space. What single cosmic mystery makes you question everything you think you know deep in the silent expanse beyond Mars? Two robotic explorers began to slow down for no reason at all. The Pioneer 10 and Pioneer 11 spacecraft, having completed their missions to Jupiter and Saturn, were now speeding toward the edge of our solar system. But scientists tracking them noticed something deeply wrong. The spacecraft were decelerating ever so slightly, as if an invisible hand was gently applying the brakes. This tiny, persistent tug was a deviation so small it was almost imperceptible, a fraction of a nanometer per second squared, yet it defied every single prediction. For decades, this pioneer anomaly became a ghost in the machine of celestial mechanics, a puzzle that refused to be solved. At first, the most logical explanations were sought. Perhaps it was a simple fuel leak from the spacecraft's thrusters creating a tiny, unintended force. Maybe it was the subtle pressure of the spacecraft's own heat radiating unevenly off their bodies, pushing them off course. Yet as each of these mundane possibilities was meticulously checked and eliminated, a more thrilling and terrifying idea began to surface. What if the laws of gravity themselves were different out there in the deep, dark void? Could this be the first hint of new physics, a crack in the foundation of Einstein's theory of general relativity? This tiny, unexplained drift became a monumental question mark hanging over our entire understanding of the cosmos. It was a classic and humbling reminder that the universe often writes its own rules, and we are merely trying to read them. That mysterious tug on the Pioneer probes was a whisper compared to the deafening roar of evidence for dark matter. We cannot see it, touch it, or even detect it with any of our instruments, yet we are certain this ghostly substance holds the very fabric of the cosmos together. Its story begins not in the deep void, but within the whirling dance of galaxies themselves. When astronomers measured how fast stars orbit the center of a galaxy, they expected a simple outcome. The stars on the outer edges, farther from the galactic core, should move slower, just as Pluto orbits the Sun much more sluggishly than Mercury. But the data revealed something astonishing. Stars on the galactic outskirts were racing just as fast as those near the center. It was as if the entire galaxy was spinning like a solid plate, a motion that defied the fundamental laws of gravity. The only possible explanation was that galaxies were embedded within vast, massive halos of something invisible, a substance whose gravity was the only thing preventing these stars from flying off into the void. This invisible scaffold, this cosmic glue, is what we call dark matter. Further proof comes from a phenomenon known as gravitational lensing. The immense gravity of dark matter warps the very space around it, bending the path of light from distant galaxies behind it. This creates distorted, stretched, and sometimes multiple images of those faraway cosmic objects, like a funhouse mirror on a universal scale. By mapping these distortions, we can literally trace the outline of the invisible, revealing the hidden skeleton of the universe. The stunning conclusion is that everything we can see, all the stars, planets, and nebulae, accounts for less than 5% of the universe's total mass and energy. Dark matter makes up over a quarter of the cosmos, a fundamental component of reality that remains utterly mysterious to our standard model of physics. We are living in a universe dominated by a ghost, a presence we can only infer by the grip it holds on everything we see. If dark matter is the ghostly glue holding galaxies together, then dark energy is the phantom force tearing the very fabric of space apart. This discovery began not with a whisper, but with a cataclysmic revelation about the fate of our entire universe. For nearly a century, scientists believed the cosmic expansion that started with the Big Bang was gradually slowing down, pulled back by the collective gravity of all the matter in existence. The ultimate question was whether this deceleration would lead to a big crunch, a fiery collapse back into a single point, or a slow, cold fade into darkness. To find the answer, two independent teams of astronomers pointed their telescopes at a specific kind of stellar explosion, a supernova that acts as a cosmic mile marker. By measuring how far away these supernovae were and how fast they were moving, they could chart the universe's expansion rate throughout its history. The data they collected was utterly shocking. The distant supernovae were much fainter than they should have been, meaning they were farther away than anyone had predicted. The inescapable conclusion was that the expansion of the universe is not slowing down at all. It is accelerating. This was like tossing a ball into the air and watching it not only fail to fall back down, but hurtle away into the sky at an ever-increasing speed. Something was overpowering gravity itself, a repulsive force woven into the vacuum of space. Scientists named this mysterious something dark energy. It is the dominant component of our universe, making up about 70% of everything that exists. Yet we have no idea what it truly is. It could be a property of space itself, a constant energy density that grows stronger as the universe expands. Or it could be a sign that our theory of gravity is incomplete on the largest scales. This single discovery completely rewrote the cosmic forecast, pointing toward a final fate far more lonely and desolate than anyone had imagined, a cold, empty expanse where galaxies are ripped apart and the last lights of the cosmos blink out one by one, forever separated by an ever-widening gulf of nothingness. This cosmic silence is perhaps the most profound puzzle of all. Our galaxy alone contains hundreds of billions of stars, and many of these are orbited by planets in the habitable zone, worlds where liquid water and the chemistry for life could exist. With numbers so staggeringly large, the universe should be a vibrant metropolis, teeming with civilizations. Statistically, the cosmos should be echoing with the signals and engineering projects of countless alien societies. Yet when we point our radio telescopes to the heavens, we hear nothing but a deafening, eternal quiet. This contradiction between the high probability of life and the total lack of any evidence is known as the Fermi paradox, and it forces us to confront some of the most unsettling possibilities about our place in the cosmos. One potential solution is the chilling concept of the Great Filter. This is the idea that at some point between the emergence of non-living matter and the development of a galaxy-spanning civilization, there exists a barrier, an evolutionary or technological challenge that is nearly impossible to overcome. This filter could lie in our past. Perhaps the spontaneous genesis of self-replicating life from simple chemistry is such an astronomically rare fluke that it has only happened once. Or the filter could be ahead of us, a looming catastrophe that inevitably destroys every advanced species before they can make their presence known. This could be something inherent to technology, like self-replicating nanomachines that consume everything, or artificial intelligence that turns against its creators. The terrifying implication is that if the Great Filter is still in our future, then our own apparent success as a species may be nothing more than a prelude to our inevitable destruction. Other explanations are less apocalyptic but equally humbling. Perhaps intelligent life is common, but it simply has no desire to communicate or expand in ways we can detect. Their goals and technologies might be so alien, so far beyond our comprehension, that we are like ants at a picnic, completely unaware of the vast, complex events happening around us. Or maybe spacefaring civilizations are fleeting, rising and falling in a cosmic blink of an eye, their signals lost in the immense ocean of time and space. The most profound and for some the most lonely answer is that there is no paradox at all. We might truly be the first or the only. In a universe of immense potential, the spark of complex, self-aware life may have only happened here, on this tiny, pale blue dot. This great silence forces us to look up at the starry void and ask not just where everybody is, but what our own noise means in the overwhelming quiet of the cosmos. Amid the profound quiet of the cosmos, a single, deafening shout once pierced the static. On a warm August evening in 1977, a radio telescope at Ohio State University, known as the Big Ear, was performing its routine scan of the heavens. Dr. Jerry Amon, a volunteer with the Search for Extraterrestrial Intelligence project, was later reviewing the computer printout, a long scroll of paper filled with columns of letters and numbers representing the faint background noise of the universe. His eyes scanned across a sequence of characters, and then he saw it. One signal was so powerful, so perfectly crafted, that it defied all natural explanation. It was a narrowband radio burst, precisely the kind of signal scientists predicted an advanced civilization would use to broadcast its existence. It came from the direction of the constellation Sagittarius, and it lasted for a full 72 seconds, the exact duration the Big Ear telescope could hold a point in the sky. Stunned, Eamon grabbed a red pen and circled the alphanumeric sequence on the printout. In the margin, he wrote a single powerful word that would echo through history. While the wow signal was by every technical measure perfect, it was billions of times stronger than the ambient radio noise of space. It was concentrated on one specific frequency, the hydrogen line, which is a fundamental electromagnetic frequency in the universe that many scientists considered a logical channel for interstellar communication. It appeared, rose to a peak, and then faded away exactly as you would expect from a signal originating from a fixed point in space as the Earth's rotation moved the telescope's gaze across it. It was the closest thing to a cosmic hello we have ever received, and then it vanished. For decades, astronomers have repeatedly pointed their most powerful radio dishes toward that same patch of sky, listening with ever-increasing sensitivity. They have scanned for any whisper, any repetition, any hint of a follow-up. The result has been a perfect, unbroken silence. The signal never returned. This singular event defies easy explanation. It was too strong to be a signal from a passing satellite or a secret military test. It did not match the profile of any known astronomical object like a quasar or a pulsar. The very perfection of its characteristics makes its disappearance the core of the mystery. A natural cosmic event would likely be repetitive, flaring up again under observation. A human-made signal would have a source we could trace. The wow signal exists in a category of its own, a 1 in a billion anomaly that has never been replicated. It stands as a tantalizing and frustrating piece of evidence, a brief, brilliant flash that forces us to wonder. Was it a fleeting malfunction of our own technology, a cosmic mirage, or was it a fragment of a message, a beacon that flickered on for just a moment, its purpose and origin forever lost to the vastness between the stars? We are left with a single word scribbled on a faded piece of paper, a ghost in the machine that continues to haunt our search for answers. While the wow signal was a fleeting burst of radio energy, another cosmic mystery announced itself through a steady, rhythmic dimming of light. Astronomers sifting through data from the Kepler Space Telescope discovered a star, officially named KIC 8462852, but better known as Tabby star, that behaved unlike anything they had ever seen. Planets orbiting a star cause predictable periodic dips in its brightness, but Tabby's star did not play by these rules. Its light would fade by enormous amounts, sometimes up to 22%, in chaotic, irregular patterns. This was not the gentle transit of a planet, which typically blocks less than 1% of a star's light. This was as if something colossal and misshapen was drifting in front of the star, blotting out its light in a way that defied all known natural explanations. The data pointed to an object or a collection of objects with a staggering total surface area, something far beyond any known swarm of comets or asteroids. The scientific community was electrified, and the most extraordinary theory quickly captured the public's imagination. Could this be evidence of an alien megastructure? The idea, first proposed by astronomer Jason Wright, suggested that an advanced civilization might have constructed a vast array of energy-collecting panels, known as a Dyson swarm, orbiting their star. Such a colossal engineering project would indeed cause the bizarre, non-repeating dimming patterns observed, while scientists considered more conventional possibilities, like a giant cloud of dust from a shattered planet or a family of incredibly large comets. Each explanation faced major hurdles. A dust cloud should glow with infrared radiation as it absorbs the star's light and heats up, but Tabby's star showed no such excess heat. The comet swarm theory required an implausibly large number of giant comets to pass in front of the star at the same time, a statistical improbability on a grand scale. The star's behavior challenged the very foundations of our models for how solar systems form and evolve. It presented a cosmic crime scene where the usual suspects had seemingly perfect alibis, leaving a void that wilder theories were all too eager to fill. The true nature of the object blocking Tabby's star remains one of the most compelling open cases in modern astronomy, a reminder that sometimes the most profound mysteries are not found in a flash of light, but in the slow, deliberate fading of it. Far out in the emptiness between galaxies, a single atomic nucleus travels at a speed so close to light that it carries the energy of a well-thrown baseball. This is not science fiction. It is an ultra-high energy cosmic ray, a subatomic bullet from the depths of space that packs a punch defying all known laws of physics. When these particles were first detected, they presented scientists with an immediate and profound paradox. According to a fundamental limit known as the Greisen-Zatsepin-Kuzmin cutoff, or the GZK cutoff for short, such particles should not be able to reach us from distant corners of the universe. The space between galaxies is not a perfect vacuum. It is filled with the faint, cold afterglow of the Big Bang, a sea of radiation called the cosmic microwave background. For a proton or an atomic nucleus traveling near light speed, this background radiation is like running through a relentless, universal hailstorm. Each collision with this radiation saps a little of the particle's energy. Over millions of light years, this energy loss should be so severe that any particle arriving at Earth with such staggering energy must have originated from a source very, very close to us, within our own galactic neighborhood. Yet when astronomers trace the paths of these cosmic cannonballs back to their points of origin, they point to vast, empty voids in intergalactic space. There are no powerful galaxies, no violent supernova, no known cosmic engines anywhere near where they seem to come from. It is as if a cannonball flew across the Atlantic Ocean and landed on a beach, but when you look back, there is no ship, no cannon, not even a hint of where it could have possibly been fired from. The sources of these particles are not just unknown, they are seemingly absent from the sky. What cosmic particle accelerator operating in the void can possibly hurl matter with such incomprehensible force? The mystery deepens with every new detection, forcing us to question whether we are missing entire chapters in the book of high-energy astrophysics. Are there colossal hidden objects in the emptiness between galaxies operating on principles we have yet to discover, or is our understanding of how matter and radiation interact across the vastness of space fundamentally and thrillingly flawed? Even the faintest glow from the birth of the universe holds a secret that threatens to unravel our most basic assumptions. The cosmic microwave background, that ancient light from the Big Bang, is the most perfect snapshot of the infant cosmos, a nearly uniform sea of radiation that fills every corner of space. For decades, it has been the cornerstone of modern cosmology, confirming that on the largest scales, the universe is isotropic, meaning it looks the same in every direction, with no special place and no preferred axis. This cosmological principle is the very bedrock upon which we have built our understanding of everything. But then we looked closer. When scientists created an incredibly detailed map of this cosmic afterglow, they discovered something deeply unsettling, an anomaly so strange it was given a dramatic name, the axis of evil. This is not a physical axis like a pole through space, but a mysterious alignment in the very fabric of the early universe. The temperature fluctuations in the cosmic microwave background, the tiny hot and cold spots that are the seeds of all future galaxies, are not scattered randomly as they should be. Instead, they appear to be aligned along a particular plane, a preferred direction that cuts across the sky. It is as if the universe has a built-in north and south, a cosmic fingerprint that points in a specific way. This discovery directly contradicts the cosmological principle. The universe, according to this map, is not the same in all directions. It has a handedness, a subtle but undeniable grain, like wood. The implications are staggering. This alignment could be a ghostly echo from a time before the Big Bang, a shadow of some deeper structure that imprinted itself on creation. Or even more radically, it could mean that our universe is not infinite and random, but is somehow shaped or constrained in a way we cannot yet comprehend. The axis of evil is a quiet, statistical whisper in the data, but it speaks of a potential revolution, a fundamental flaw in the story we tell ourselves about the nature of reality itself. The universe's first recipe seems to have left out a key ingredient. In the fiery forge of the Big Bang, during its initial 3 minutes, the fundamental elements of hydrogen, helium, and a tiny trace of lithium were forged. This process, known as Big Bang nucleosynthesis, is one of the most precisely tested pillars of modern cosmology. The theoretical models predicting how much of these elements should have been created are exquisitely detailed, and for hydrogen and helium, the predictions match the observed abundances in the oldest stars almost perfectly. But for lithium, the numbers are catastrophically wrong. The oldest stars in our galaxy, which form from the pristine, uncontaminated gas of the early universe, should contain about 3 times more lithium than what we actually measure when we analyze their light. It is a discrepancy that cannot be explained away by observational error. The universe's primordial cookbook is missing a page, and it points to a fundamental gap in our knowledge of physics itself. This is not a small accounting error. It is a direct challenge to our understanding of what happened in the universe's very first moments. Could our models of the Big Bang be incomplete? Perhaps an unknown form of matter, like a certain type of neutrino, interacted with the primordial soup and destroyed some of the lithium as it was forming. Or maybe our understanding of the nuclear reactions themselves is flawed, missing a key channel that would have depleted the lithium. Another possibility pushes the mystery forward in time. Perhaps these ancient stars are not the pristine time capsules we believe them to be. Maybe they have internal processes, some slow-burning nuclear fusion deep in their cores that systematically destroy lithium over their immensely long lives. Yet no conventional stellar model can explain the sheer consistency of the lithium deficit across so many different stars. This lithium problem is a quiet but persistent thorn in the side of cosmology. It tells us that even in our most successful theories, there can be a subtle crack, a single wrong number that hints at an entire hidden layer of physics waiting to be discovered. We are left staring at the oldest stars in the sky, witnessing a fossil record that defies the very story we tell about their creation. The quiet, persistent anomalies of the cosmos sometimes give way to a storm of human controversy. Deep within a laboratory, a device shaped like a simple metal cone sat on a sensitive balance. When researchers pumped microwaves into its sealed chamber, the entire apparatus seemed to push ever so slightly against one direction. This was the M-drive, an engine that by all rights should not work. It proposed a way to create thrust without expelling any propellant whatsoever, a concept that directly and brazenly violates one of the most fundamental laws of physics, Newton's third law of motion. For every action, there's an equal and opposite reaction. Rockets work by throwing mass backward to lurch forward. The M-drive, with no mass to throw, appeared to be a perpetual motion machine in disguise, a magic trick that defied the very conservation of momentum. The initial claims were met with a wall of skepticism, as they should have been. The measured thrust was minuscule, and critics argued it was likely an experimental artifact. Perhaps heat from the microwaves was causing air currents inside the vacuum chamber, pushing on the scale. Maybe it was an interaction with the Earth's magnetic field, or a subtle vibration that the instruments misinterpreted. The scientific process demanded rigorous, independent replication, and for years, teams around the world tried. Some reported a similar, tiny thrust. Others found nothing at all. The results were frustratingly inconsistent, trapped in a gray area just at the edge of detectability. The controversy raged not over a proven phenomenon, but over the ghost of one, a signal dancing in the noise. Yet the implications of its validation were so profound that they could not be ignored. If the M-drive truly worked, it would not just be a new kind of engine. It would be a revolution. It would mean that our understanding of physics, a framework that has held for centuries, was missing a critical piece. It could hint at a way to manipulate inertia or tap into quantum fluctuations in the vacuum of space itself. A working propellantless drive would utterly transform space travel, allowing spacecraft to accelerate continuously for months or years, reaching the outer planets in weeks and the nearest stars within a human lifetime. The dream of a true starship hung in the balance of those contentious, finicky experiments. Ultimately, after years of debate and more careful testing, the scientific consensus has largely settled. The thrust was an illusion, a complex measurement error, but the story of the M-drive is far from a failure. It is a powerful testament to a different kind of law, the law of how science corrects itself. It shows that even when we desperately want something to be true, when it promises to unlock the stars, the universe demands evidence that can withstand the harshest scrutiny. The M-drive was a beautiful, tantalizing idea that broke the rules, but in the end, the rules of scientific inquiry proved stronger. Even our most precise tools for measuring the cosmos are now telling us two different, conflicting stories. This is the Hubble tension, a crisis brewing at the very heart of modern cosmology. To understand the problem, you need to know the two main ways we measure how fast the universe is expanding, a number called the Hubble constant. The first method is like using a cosmic fossil. We look at the ancient light from the cosmic microwave background, the afterglow of the Big Bang itself. By meticulously mapping its tiny temperature fluctuations, we can calculate how fast the infant universe was expanding, and then run the clock forward using our best models of dark matter and dark energy to predict what the expansion rate should be today. This gives us one very precise number. The second method is like using a local speedometer. We look at relatively nearby galaxies and use stars called Defied variables as cosmic mile markers. These special stars pulse at a rate that is directly tied to their true brightness. By measuring how fast they pulse, we know their true brightness, and by comparing that to how dim they appear from Earth, we can calculate their distance with incredible accuracy. When we combine these distances with measurements of how fast these galaxies are moving away from us, we get a direct, modern reading of the expansion rate. This gives us a second, equally precise number. The crisis is this: these two numbers do not agree. The local measurement using Cepheids and supernova says the universe is expanding significantly faster today than the fossil light from the early universe predicts it should be. The discrepancy is not large, only a few percent, but with our measurements now so exquisitely refined, that small gap is a chasm. It is like predicting how fast a car should be going based on the power of its engine, only to point a radar gun at it and find it is moving noticeably quicker. This is not a simple measurement error. This is a direct conflict between two of the most trusted pillars of cosmology. Something is fundamentally wrong. Either our reading of the cosmic fossil is incorrect, or our local speedometer is broken, or our entire understanding of the physics that connects the early universe to the present day is missing a crucial ingredient. This tension points toward the need for new physics, perhaps a new form of dark radiation that existed in the early universe, or a property of dark energy that changes over time. It is a humbling reminder that the universe, even in its most basic behavior, still holds profound secrets that defy our most careful calculations. Even our established laws of physics suggest that their own rules are incomplete. This leads us to a concept so strange it seems to belong in a world of pure imagination: the hypothesis of unparticles. Imagine a substance that is not made of discrete, individual particles like electrons or quarks, but behaves as a continuous, indivisible whole. This is the essence of unparticle physics, a speculative idea proposing a hidden sector of reality that operates outside our standard model. Unlike anything we know, unparticle stuff would not have a specific mass or exist at a definite scale. Its behavior will be governed by strange fractional dimensions, making it seem like a fog that has weight and influence, yet cannot be broken down into constituent parts. How could such a thing exist? The mathematics suggests that at incredibly high energies, perhaps moments after the Big Bang, a special kind of symmetry existed in the universe. As the cosmos cooled, this symmetry broke, leaving behind a hidden scale invariant sector. The effects of this unparticle stuff would be ghostly but profound. It could mediate new, incredibly weak forces between ordinary matter, or it could be the mysterious dark matter that binds galaxies together. Its most baffling property is scale invariance. A cloud of unparticles would look and behave the same, whether you observed it from a distance of a millimeter or a light year, defying our everyday intuition about how objects should change with size. This is not just a new particle, it is a new state of being for matter itself. While still a theoretical ghost, the unparticle hypothesis provides a potential key for unlocking several cosmic puzzles, from the strange results of certain particle collisions to the missing lithium in the early universe. It represents a frontier where physics willingly steps into the unknown, proposing that the true fundamentals of reality might be far more fluid and alien than the neat, particulate universe we think we know. Deep within the heart of a black hole, a law of the universe is seemingly broken, not by a force but by a paradox. The conflict between Einstein's theory of gravity and the rules of quantum mechanics reaches its peak with a question that sounds simple, yet has profound implications. What happens to the information about an object that gets swallowed by a black hole? According to the quantum rule of unitarity, information can never be truly destroyed. It can be scrambled, transformed, or hidden, but it must in principle be recoverable. This is a fundamental tenet of reality, like saying 2 + 2 must always equal 4. The information about every particle that formed a star, a book, or a person must persist in some form. But for decades, black holes appeared to be cosmic shredders, violating this sacred rule. The crisis began with Stephen Hawking's revolutionary discovery. He realized that black holes are not completely black. Due to weird quantum effects happening right at the edge of the event horizon, they slowly leak a faint glow of radiation. This Hawking radiation is incredibly subtle, but it has a devastating consequence. As the black hole radiates, it loses mass, slowly evaporating over trillions of years until it potentially vanishes entirely. The problem is this: the Hawking radiation itself is completely random, a featureless hiss of thermal energy. It carries no information about what fell into the black hole. So if the black hole evaporates and disappears, what happened to all the information about the star that collapsed to form it, or the spaceship that foolishly crossed its horizon? The information seems to have been erased from existence, a direct violation of quantum law. This is the black hole information paradox. For years, physicists were faced with a terrifying choice. Either our understanding of quantum mechanics was wrong and information could be destroyed, or our understanding of gravity was wrong and black holes did not work the way we thought. How could two of our most successful and beautiful theories of physics be so fundamentally at odds? The search for the universe's ultimate particle accelerator has turned into a cosmic manhunt. Focus has narrowed onto the most violent and energetic objects known to exist: active galactic nuclei. At the heart of some distant galaxies, a supermassive black hole, weighing billions of times more than our sun, is actively feeding. As vast clouds of gas and dust spiral into this gravitational abyss, they don't just vanish quietly. The material is heated to millions of degrees, creating a raging whirlpool of plasma that can shoot out colossal jets of radiation and matter, stretching for thousands of light years into space. These jets are nature's own particle beams, and for a long time, they seem like the perfect suspects, the only engines powerful enough to potentially launch those ultra-high-energy cosmic rays across the universe. Yet when astronomers meticulously traced the paths of the cosmic rays back to their points of origin, they found a frustrating mismatch. The rays did not consistently point back to the brilliant, obvious hearts of these active galaxies. Instead, their trajectories often led to empty space or to quieter, less violent galaxies that should not possess the necessary power. It was like finding a fingerprint at a crime scene that belongs to no one present. This has forced scientists to consider even more exotic possibilities. Could the sources be something we have not yet even classified, like a new type of hypernova or a collision between dark matter particles? The detective work now involves building ever larger and more sensitive observatories, like the Pierre Auger Observatory in Argentina, which uses thousands of square kilometers of desert as a giant detector. It watches for the faint expanding showers of particles created when a single cosmic ray bullet slams into our atmosphere. By mapping the arrival directions of millions of these events, physicists hope to finally see a pattern emerge from the chaos, a clustering of points on the sky that will point unmistakably to the hidden lair of these cosmic outlaws. The mystery of their origin is no longer just about finding an object, but about understanding a fundamental process. What hidden physics, operating in the dark voids between galaxies, can possibly bend the rules of reality to achieve such impossible energies? From the slow evaporation of black holes, we now turn to a phenomenon that explodes into existence and vanishes in an instant. Fast radio bursts are the universe's most brilliant and baffling flashes, packing the energy of 500 million suns into a pulse that lasts less than the blink of an eye. The first one was discovered in 2007, buried in archive data from the Parkes Radio Telescope in Australia. It was a single spectacular spike of radio waves, a cosmic shout that came and went in just 5 milliseconds. For years it was considered a possible fluke, an anomaly from an instrument on Earth, but then more were found. These bursts are not just rare, they are fleeting, appearing at random times from random directions across the sky, making them nearly impossible to predict and incredibly difficult to catch in the act. The central mystery is one of sheer power. What natural process can possibly release such an immense amount of energy so quickly? The leading theories are almost as dramatic as the bursts themselves. One of the most popular ideas involves the dead stars known as magnetars. These are neutron stars with magnetic fields so intense they could strip the information from a credit card from halfway across the solar system. A starquake on the surface of a magnetar, A sudden cracking of its crust could unleash a titanic magnetic shockwave, rippling out into space as one of these brilliant radio flashes. Another possibility is the cataclysmic merger of two neutron stars, spiraling into each other and collapsing into a black hole in a final, energetic death rattle. Yet for all the violence of these cosmic events, they struggle to fully explain the sheer diversity of the bursts we now observe. Some FRBs are one-off events, a single solitary blast from the dark. Others are repeaters, firing off multiple signals from the same location, a behavior that rules out any source that destroys itself in the process. This repeating nature is what fuels the most speculative and thrilling explanation. Could we be witnessing the leakage from unimaginably powerful deep space engines? Some have proposed that these bursts could be the side effect of light sails, propelled by alien civilizations using focused radio beams to push spacecraft to near light speeds. The beam would sweep across the sky, and from our distant vantage point, we would see it as a blinding, milliseconds-long flash. While this remains a fringe hypothesis, it underscores just how defiant these signals are of easy classification. There are cosmic fireflies flashing in the dark, each brief glimmer a profound question about the limits of physics and the potential for wonders we have only begun to dream of. The silent, fleeting bursts of radio energy were not the only unexpected visitors to our cosmic neighborhood. In October 2017, astronomers at the Pan-STARRS Observatory in Hawaii spotted a faint point of light moving at a staggering speed. It was the first object ever detected that had come from beyond our solar system, a true interstellar wanderer. They named it Oumuamua, a Hawaiian word meaning a messenger from the distant past arriving first. This messenger was unlike anything we had ever seen. As telescopes around the world swiveled to track it, they revealed an object defying all expectation. It was not a typical roundish comet or asteroid. Its light curve, the pattern of its brightness as it tumbled, showed extreme variations, suggesting an absolutely bizarre shape. Oumuamua appeared to be highly elongated, perhaps 10 times as long as it was wide, a spinning cosmic cigar or a flattened pancake tumbling through the void. No natural object we know of in our own solar system has such a dramatic form, but the strangeness did not stop with its silhouette. As it raced away from the sun, something impossible happened. Its trajectory could not be explained by gravity alone. It was accelerating ever so slightly, as if it had a gentle push from within. For comets, this is a common phenomenon called outgassing. The sun's heat vaporizes ice on the surface, creating jets of gas that act like tiny thrusters. The problem was, Oumuamua showed no visible signs of outgassing. No surrounding cloud of gas and dust, no tail. It was a rocket with no visible exhaust, a car accelerating with its engine silent. This non-gravitational acceleration forced scientists to confront a puzzle with no easy answer. If it was outgassing, why was it so clean, leaving no dusty trail? Could the pressure of sunlight itself, photon pressure, be pushing on such a large, thin object? That seemed far-fetched. The lack of a simple, observable cause opened the door to more speculative ideas, including the controversial suggestion from Professor Avi Loeb that it might be a piece of alien technology, a light sail from a distant civilization. While most astronomers favor a natural explanation, perhaps involving a cloud of pure hydrogen gas that is invisible to our telescopes, the truth is that Oumuamua's peculiar properties defy our current categories. It was a visitor that followed the rules of physics just enough to be detected, but broke all the rules of convention, leaving behind a trail of questions as it faded back into the interstellar dark. Even the smallest particles in the universe hold secrets that mock our understanding of space and time. Two particles can be born together, linked in a quantum marriage, and then flung to opposite ends of the cosmos. Yet the moment you measure a property of one, like its spin, its distant partner instantly assumes the opposite spin, no matter how many light years separate them. This is quantum entanglement, a phenomenon so bizarre that even Albert Einstein rejected its implications, famously calling it spooky action at a distance. He believed this spookiness was proof that quantum mechanics was an incomplete theory, because in his universe, nothing, not even information, could travel faster than light. This instantaneous connection seemed to violate the very bedrock of his theory of relativity. The spookiness lies in the fact that the particles do not simply have a predetermined, hidden setting that we are just discovering. Before measurement, their properties like spin or polarization are genuinely undefined, existing in a blur of all possible states. The act of observing one particle here doesn't just reveal its state, it seemingly forces its twin, instantly and with absolute certainty, into the correlated state over there. It is as if you had a pair of magical gloves. You put each glove in a separate box and mail one to a distant galaxy without looking. The moment the recipient opens their box and sees a left-handed glove, your unopened box back on Earth instantly and irrevocably contains the right-handed one. The gloves were not predetermined. Your act of observation on one side of the universe defined the reality for the other. This challenges our most basic intuition about locality, the idea that objects are only influenced by their immediate surroundings. Entanglement suggests a deeper, hidden layer of reality where everything is fundamentally interconnected, a cosmic web that operates outside our familiar notions of here and there. For decades, physicists debated whether this was truly happening or if there were hidden variables at play. Then in the 1970s, physicist John Bell devised a mathematical test, and subsequent experiments have confirmed again and again that the spooky action is real. The universe at its most fundamental level is non-local. This does not, however, allow for faster-than-light communication. While the correlation is instantaneous, the result you get from measuring your particle is completely random. You cannot control whether you get a left or right-handed glove, so you cannot send a meaningful message. The universe, it seems, prevents paradox by allowing for a strange, intimate connection that is useless for sending a signal, yet profound for shaping the very nature of reality itself. We are left with a cosmos that is far more deeply and mysteriously intertwined than our classical minds can comfortably grasp. This spooky interconnectedness exists within a vacuum that is anything but empty. According to our best theories, the void of space should be a seething, bubbling foam of virtual particles. These are pairs of particles and antiparticles that spontaneously pop into existence from nothing, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and vanishing. This quantum jitter should imbue every cubic centimeter of empty space with a colossal amount of energy, a background hum of pure power known as vacuum energy. This is where our theory and our reality violently diverge in the most spectacular miscalculation in all of science. When physicists calculate the theoretical energy density of this quantum vacuum, the number they get is staggeringly large. Then they measure the actual energy density of empty space, which we observe as the force of dark energy driving the universe's accelerated expansion. The two numbers should be the same, but they are not even close. The theoretical prediction is wrong by a factor of 10 to the power of 120. This number is so incomprehensibly vast that it defies all human analogy. It is not just a few zeros off. It is a number greater than the total number of atoms in the entire observable universe. If this theoretical value were correct, the repulsive force of the vacuum would have been so immense that it would have ripped every single atom, every star, every galaxy apart in the first instant after the Big Bang. Our universe and we ourselves would simply never have had a chance to exist. The fact that we are here to ponder this at all means our prediction is catastrophically wrong. This vacuum catastrophe represents a fundamental chasm in our understanding, a screaming disagreement between the world of the very small, governed by quantum mechanics, and the world of the very large, ruled by gravity. It suggests that something is deeply missing from our picture, perhaps a symmetry or a cancellation mechanism we have not yet discovered that almost perfectly, but not quite completely, nullifies the vacuum's ferocious energy. This is not a small error in the margins. It is a sign that our most fundamental theories of reality are standing on a foundation we do not yet understand. The silent, unseen hand that gently tugged at the Pioneer probes has a close cousin, a fleeting ghost that haunts our very doorstep. During precise gravitational slingshot maneuvers around Earth, several spacecraft have experienced a tiny, inexplicable kick. As a probe like Galileo or Rosetta swings past our planet, using its gravity like a cosmic whip to gain speed and change trajectory, its velocity is tracked with incredible precision. Yet time and again, the final speed is just a few millimeters per second off from what our most detailed models predict. This is the flyby anomaly. It is a deviation so minuscule it seems trivial, but in the high-stakes world of interplanetary navigation, where error of a single centimeter per second can mean missing a distant world by thousands of miles. This tiny mismatch is a glaring red flag. The anomaly does not happen on every flyby, and its effect seems to change, sometimes adding speed, sometimes subtracting it in a way that defies a simple pattern. Scientists have chased every conceivable explanation. Could it be an unaccounted for effect from Earth's atmosphere? Even at high altitudes, perhaps the planet's rotation creates a subtle, complex drag that our models miss. Maybe it is a hint that our understanding of Earth's own gravity field, with its slight lumps and bumps, is not quite perfect. Yet after meticulously checking and refining these factors, the stubborn little error persists. It is as if the universe is adding a secret, unsanctioned ingredient to the recipe for gravity, a whisper of a force that only reveals itself during these specific, high-velocity celestial dances. This recurring glitch in our planetary calculations forces a humbling admission. Even here in our own gravitational backyard, a fundamental piece of the puzzle might be missing, suggesting that for all our mastery of orbital mechanics, a deeper layer of physics remains just beyond our grasp. Even the most perfect snapshot of the infant universe contains a blemish that should not exist. Within the faint glow of the cosmic microwave background, one region stands out as profoundly and unsettlingly cold. This is the CMB cold spot, a vast circular patch in the constellation Eridanus that is significantly colder than its surroundings. The temperature difference is minute, only a few millionths of a degree, but its size is what makes it a genuine anomaly. It stretches over 1 billion light years across, a cosmic bruise on the sky that is far too large and far too cold to be explained by random chance alone. At first, astronomers thought they had a simple answer. They proposed that this cold spot was a shadow cast by a supervoid, an enormous region of space that is mostly empty, containing far fewer galaxies and clusters than the cosmic average. Light traveling through such a void would lose a tiny amount of energy as it climbed out of the void's weakened gravitational well, a phenomenon known as the integrated Sachs-Wolf effect. This energy loss would manifest as a slight cooling in the background radiation. It was an elegant solution, but the universe refused to cooperate. When they went looking for this proposed supervoid, they found one, but it was not nearly big enough or empty enough to account for the dramatic temperature drop observed. The void is like a shallow dip in the road, yet the temperature anomaly suggests we should be seeing the aftermath of a massive crater. This mismatch between cause and effect is the core of the mystery. If the void did not cause the cold spot, then what did? This is where the explanations must venture into truly exotic territory. One of the most mind-bending possibilities is that the cold spot is a cosmic scar, the imprint of a collision with a parallel universe in the vast multiverse. In this scenario, just after the Big Bang, our budding universe may have bumped into another bubble universe. The energy drained away from that point of contact could have left our universe with a permanent cold patch, a fossilized record of that primordial encounter. Other theories remain within our own universe but push the boundaries of known physics. Perhaps the cold spot is the signature of a cosmic texture, a flaw in the structure of space-time itself that formed as the fundamental forces of the universe froze into place. These textures would be knots of concentrated energy, and the unraveling of one could have released a shockwave that left this cold imprint on the cosmos. Or it could be evidence of an early hyperinflationary phase that happened in a way we do not yet understand. The CMB cold spot endures as a quiet, colossal question mark. It is a reminder that our most comprehensive map of reality may still be missing entire continents of understanding, hidden in the faintest of cosmic whispers. The rules governing the atomic nucleus are among the most robust in all of physics, yet even here, nature seems to be testing the limits. Deep within particle accelerators, scientists have witnessed signatures of something that should not be. It is a ghostly configuration known as a tetraneutron, a cluster of 4 neutrons bound together in a fleeting embrace. According to our fundamental understanding of nuclear forces, this is impossible. The strong nuclear force which glues protons and neutrons into atomic nuclei is a social glue. It works best in a mix, binding protons and neutrons together. Systems of just neutrons without any protons to balance the interaction are not supposed to be stable. The nuclear models that have served us so well for decades predict that a group of neutrons should simply fly apart instantly, unable to form any kind of bound state. The very idea of a tetraneutron defies this foundational principle. The evidence first emerged from experiments where scientists smashed a nucleus of beryllium into a carbon target. In the aftermath, they detected the debris from a specific reaction that seemed to leave behind a single unified particle with the exact energy and properties of 4 neutrons sticking together. This was not a stable atom, but a resonant state, a temporary arrangement that existed for just a fleeting moment, perhaps a mere 10 to the power of negative 22 seconds before it disintegrated. The scientific community reacted with profound skepticism. Could this be an experimental illusion, a chance alignment of 4 separate neutrons that merely looked like one particle? The hunt was on for a repeatable, unambiguous observation. Subsequent experiments using different methods and more sophisticated detectors have continued to report similar signals, each one strengthening the case that we are seeing a real, albeit ephemeral, phenomenon. If the tetraneutron is confirmed, it would force a dramatic rewrite of nuclear theory. It would mean that the nuclear force can operate in a way we never anticipated, capable of creating bonds in a pure neutron environment. This would have staggering implications for our understanding of the most extreme objects in the cosmos, like neutron stars. These incredibly dense corpses of dead stars are essentially giant atomic nuclei, composed almost entirely of neutrons. The possibility of neutron clusters forming within them could change our models of their internal structure and behavior. The tetraneutron conundrum is a tiny, fleeting signal in a detector, but it points to a vast and hidden landscape of nuclear physics, a realm where the rules we thought were absolute may only be the beginning of the story. A strange and persistent glow emanates from the very heart of our galactic home. For over a decade, astronomers have been piecing together a map of the sky using gamma rays, the most energetic form of light in the universe, and they found something brilliant and baffling at the center of the Milky Way. There is a powerful, diffuse excess of this radiation, a gamma ray fog that should not be there. At first, the most logical suspects were ordinary, if extreme, cosmic objects. The galactic core is a crowded, violent place, teeming with pulsars, the rapidly spinning corpses of dead stars that beam out radiation like cosmic lighthouses. Yet when scientists meticulously counted and modeled the expected output from all these known sources, the numbers fell dramatically short. The glow was far too intense and too smoothly distributed to be explained by a collection of individual pulsars. It was as if you were standing in a forest at night and you could see the distinct flashing lights of hundreds of fireflies, but the entire sky above you was also cast in a uniform, eerie luminescence that had no single source. This galactic center excess is that universal glow, and its presence points to a far more exotic culprit. The leading theory is that we are witnessing the final, fiery death throes of dark matter itself. According to this idea, dark matter particles are not completely isolated. When 2 of them collide in the dense environment of the galactic center, they could annihilate each other in a flash of pure energy, converting their mass directly into gamma rays. If this is true, then this faint, pervasive glow is not just a mysterious signal. It is the first indirect glimpse of the universe's most elusive substance, the ghost finally revealing itself not by its gravity, but by its self-destruction. The implications are staggering. Catching dark matter in the act of annihilation would allow us to finally understand its properties, to weigh it, and to know how it interacts with itself. It would be a monumental leap, transforming dark matter from a theoretical phantom into a tangible particle that we can study, yet the case is not yet closed. The signal is frustratingly ambiguous, and some researchers still hold out hope that an undiscovered population of ultra-faint pulsars could be the source. The hunt now focuses on finding a smoking gun. If the glow is from dark matter, it should also appear in the centers of nearby dwarf galaxies and as a faint halo around our own galaxy. If it is from pulsars, the gamma rays should be pinpointed to specific fixed locations in the sky. We are left watching the core of our galaxy, waiting for the universe to deliver its verdict on whether we are seeing the last light of a cosmic ghost or simply a new class of star we have yet to fully understand. The ghostly glow from our galaxy's heart is a cosmic clue, but a far more precise anomaly is brewing within the very particles that make up reality. Deep beneath the Illinois prairie at the Fermi National Accelerator Laboratory, scientists have spent years measuring the wobble of a particle called the muon. A muon is a heavy, unstable cousin of the electron, and like a tiny spinning magnet, it possesses a property known as a magnetic moment. The rate of its wobble in a magnetic field is one of the most exquisitely calculated numbers in all of physics, predicted by the Standard Model, which is our comprehensive rulebook for the subatomic world. The theory is so precise it's like predicting the exact number of grains of sand on a mile-long beach, yet when physicists at Fermilab completed their latest experiment, their painstaking measurements revealed a tiny, stubborn discrepancy. The muon's wobble was ever so slightly stronger than the rules said it should be. This deviation is known as the anomalous magnetic moment. The difference is minuscule, a fraction of a percent, but in the world of particle physics, such a precise mismatch is a screaming siren. It is not a flaw in the experiment, but a crack in the foundation of the Standard Model itself. This tiny wobble suggests that the muon is feeling the influence of something not in our current physics catalog. As the muon spins, it is constantly emitting and absorbing a cloud of virtual particles from the quantum foam. The Standard Model accounts for all the known particles in that cloud. But the unexpected strength of the wobble implies there is an additional, unseen particle in that cloud, tugging on the muon, or perhaps a completely new force of nature subtly altering its behavior. It is as if you were perfectly balancing a scale with known weights, but the scale still tips, revealing the presence of an invisible object resting on one side. This anomaly is arguably the most compelling hint we have that our universe is populated by more than just the particles and forces we have already discovered. The implications are profound. That tiny, persistent wobble could be our first indirect detection of supersymmetric particles, long theorized candidates for dark matter. Or it could point to hidden dimensions or other exotic physics lying just beyond our current reach. This is not a mystery from the distant cosmos, but one written in the dance of a fundamental particle, a whisper from the quantum void that our most perfect theory of the small-scale world is incomplete. Our cosmic neighborhood rests inside a staggering emptiness, a billion light-year-wide bubble of near-nothingness. This is the KBC void, named for the astronomers who discovered it, and its existence places us in a disturbingly special location. The cosmological principle, that foundational idea that the universe is uniform and has no center, insists that matter should be spread evenly when you look at large enough scales. Yet here we are living in one of the largest underdense regions ever mapped, a cosmic backwater of profound quiet. Imagine the universe as a bustling metropolis with galaxies clustered like skyscrapers in a dense downtown. According to the rules, we should be living in one of those bright, crowded districts, but instead our Milky Way is situated in a vast, dark suburban sprawl, a sparse region where the galactic neighbors are few and far between. The sheer scale of this void makes its existence wildly improbable. Finding such a colossal emptiness right at our doorstep forces a humbling reconsideration of our place in the cosmos. Are we truly just a random speck in a uniform universe? Or does our address in this great cosmic expanse carry a significance we are only beginning to grasp? This void around us whispers that the universe might not be so featureless after all, and that our position within it could be far more unique than we ever dared to believe. If a black hole is a cosmic drain from which nothing returns, its theoretical twin is a cosmic fountain. This is the white hole, a bizarre and beautiful solution to Einstein's own equations of gravity that turns the logic of a black hole completely inside out. Where a black hole's event horizon is a point of no return, a one-way street into oblivion, a white hole's horizon would be an exit door that nothing can ever enter. It would only emit energy and matter, violently spewing out light and particles in a perpetual outburst of creation. Think of it as a video of a black hole played in reverse, a universe vomiting instead of swallowing. Yet for all its mathematical elegance, the white hole presents a paradox so severe that most physicists dismiss it as physically impossible. Its existence would shatter one of the most fundamental laws we know, the second law of thermodynamics. This law states that the universe on the whole must always move from order to disorder, that entropy must always increase. A white hole, by spontaneously generating and ejecting ordered energy, would be like a shattered glass reassembling itself and leaping back onto the table. It would be a pocket of the cosmos where entropy mysteriously and impossibly decreases. Furthermore, a white hole disrupts the very flow of cause and effect in space-time. In our reality, causes always come before their effects. A white hole's behavior, erupting without any prior cause or intake of material, would be an effect without a cause, a cosmic violation of causality itself. So why do we even entertain such a rule-breaking idea? White holes remain a tantalizing ghost in the machine of general relativity, a reminder that the mathematics of our universe can sometimes paint pictures of realities that the physics itself forbids. They are a stunning testament to the fact that the cosmos, even in theory, holds symmetries and possibilities that defy our everyday experience of time and order. Einstein could never accept the spooky nature of the quantum world. That deep-seated conviction led him, along with his colleagues Boris Podolsky and Nathan Rosen, to formulate a brilliant thought experiment designed to prove that quantum mechanics was an incomplete theory, that a deeper, more sensible reality must exist underneath the weirdness. This is the EPR paradox, and its implications shake the very foundation of what we consider to be real. Their argument was rooted in two very reasonable principles that have guided science for centuries. The first is the principle of locality, the idea that objects can only be influenced by their immediate surroundings, and that no information or influence can travel faster than light. The second is the principle of realism, the belief that the universe exists in a definite state whether we are looking at it or not. An electron has a specific spin, a particle has a precise position, all independent of any measurement. Einstein and his team imagined a pair of entangled particles flying apart from each other. According to quantum mechanics, their properties like spin remain in a fuzzy superposition until one is measured. The instant you measure particle A and find it spinning up, particle B instantly becomes spinning down. Einstein argued that this spooky action at a distance was absurd. How could particle B possibly know what happened to particle A light years away without some signal breaking the cosmic speed limit? He concluded that the only logical explanation was that both particles carried with them hidden instructions from the moment they were created. They must have had definite, predetermined spins all along, and quantum mechanics was simply ignorant of these hidden variables. The EPR paper was a powerful challenge, a defense of a common-sense universe where things have properties and influences travel at a finite speed. For decades, it seemed like a philosophical debate without a clear resolution. Then, in the 1960s, physicist John Bell found a way to test it. He devised a mathematical theorem that could distinguish between Einstein's hidden variables and the truly spooky quantum view. If hidden variables were real, the correlations between entangled particles would fall within a certain limit. If quantum mechanics was correct, they would violate that limit. When the experiments were finally performed, the results were unequivocal. The quantum view won. There are no hidden instructions. The particles do not have predefined properties. This forces us into a breathtaking, and for some, an uncomfortable conclusion. Reality is not locally real. The universe is not a collection of objects with fixed properties waiting to be discovered. Instead, properties like position and spin are literally created by the act of measurement itself. The moon is not there when nobody looks, as one physicist famously quipped. This is not just a quirk of tiny particles. This is a statement about the fundamental nature of existence. The EPR paradox began as an attempt to restore classical order, but it ended up revealing a cosmos far stranger and more interconnected than Einstein could have ever dreamed. A universe where observation is not a passive act, but a creative one. Far beyond the orbit of Neptune, in the frigid darkness of the Kuiper belt, a collection of small, icy worlds is behaving as if they are under a spell. These distant objects follow wildly elongated orbits, all pointing in roughly the same direction and tilted at a similar angle to the plane of the solar system. This orbital alignment is no random coincidence. It is as if an unseen shepherd, a ghostly gravitational hand, is herding them, guiding their paths to the void. The mathematical probability of this clustering happening by chance is astronomically low. This is the compelling evidence for a hypothetical giant, a world we call Planet 9. This would be no ordinary planet. Theorists suggest it could be a super-Earth, a world up to 10 times the mass of our own, tracing a vast and lonely path around the sun, taking perhaps 10,000 or even 20,000 years to complete a single orbit. Its gravitational influence will be the only way to explain why these distant Kuiper belt objects are not scattered randomly. but are instead grouped together like iron filings aligning to a hidden magnet. The hunt for this phantom world is one of the greatest modern astronomical quests. Teams of researchers are meticulously scanning the darkest reaches of our own celestial backyard, using the world's most powerful telescopes to find a single faint point of light moving slowly against the background of fixed stars. It is a search for a needle in a cosmic haystack, a shadow that has so far remained perfectly hidden. If found, Planet 9 would be a discovery that shatters our models of solar system formation. How could such a massive world end up so far from the Sun? Our standard theories suggest the giant planets, Jupiter, Saturn, Uranus, and Neptune, formed closer in and then migrated to their current positions. But a planet of this size in such a distant orbit is a complete anomaly. It may be an exiled world, violently flung outward by a gravitational tug of war with Jupiter in the solar system's chaotic youth. Or even more radically, it could be a rogue planet, an interstellar wanderer that was captured by our sun's gravity long ago, becoming a permanent, if reclusive, member of our cosmic family. Its existence would force a complete rewrite of our solar system's history, revealing a past far more dynamic and violent than we ever suspected. We are left looking at the strange dance of icy rocks in the dark, wondering what colossal companion, what unseen king of the outer darkness is orchestrating their silent, synchronized ballet from the shadows. The ghostly presence of dark matter leaves its signature not just in the speed of stars, but in the very bending of light itself. When astronomers train their telescopes on immense galaxy clusters, they witness a cosmic mirage. The collective gravity of a cluster is so powerful that it warps the fabric of space-time around it, acting like a giant lens that distorts and magnifies the light from galaxies billions of light years behind it. This phenomenon, called gravitational lensing, creates stretched, twisted, and often multiple images of those background galaxies, painting ethereal arcs of light across the sky. But sometimes the lens reveals something far more profound. The bullet cluster provides perhaps the most stunning visual evidence for dark matter ever captured. This system is not one, but two colossal galaxy clusters that have violently collided and passed through each other. During such a collision, the clouds of hot gas, which make up most of the normal, visible matter, slam together and slow down due to friction, like two clouds of smoke merging. The dark matter, however, does not interact with itself or the gas. It is completely invisible and frictionless, so while the visible gas got stuck in the middle of the collision, the dark matter from both clusters simply sailed right through, unaffected. When scientists mapped the cluster's total mass using gravitational lensing, they found a shocking separation. The peaks of the mass distribution, the true gravitational centers, were not where the glowing gas was. They were offset, located in the regions now dominated by the galaxies that had also passed through. The lensing effect showed that most of the mass was floating in empty space, completely divorced from the normal matter. This observation delivers a devastating blow to theories that try to explain galactic motions by modifying the laws of gravity. If gravity were simply stronger on large scales, as those theories suggest, then the lensing should always be strongest where the visible matter is most concentrated. But the bullet cluster proves that is not the case. The gravity and therefore the mass is somewhere else entirely. It is a direct observational confirmation that the universe is filled with a substance that does not emit, absorb, or reflect light, a substance that interacts with our world only through the silent, persistent pull of gravity. We are not just mapping the invisible, we are watching it move through the visible universe, a ghost that walks through walls without leaving a trace. A dead star is locked in a silent, desperate struggle against its own weight. This is the story of a neutron star, the densest object in the universe that can still resist the final pull of oblivion. When a massive star explodes in a supernova, its core collapses. If that core is between about 1.4 and 2.1 times the mass of our sun, it does not become a black hole. Instead, the force of gravity is so immense that it crushes atoms themselves, fusing protons and electrons together to form a solid ball of neutrons. The result is a city-sized object with the mass of a star, a single teaspoon of which would weigh billions of tons on Earth. For decades, physicists have calculated a strict boundary for these cosmic corpses, a point of no return known as the Tolman-Oppenheimer-Volkoff limit. Beyond this theoretical line, the pressure from the neutron degeneracy, the fundamental quantum force that holds the star up, simply fails. the star can no longer support its own mass and collapses instantly, vanishing behind an event horizon to become a black hole. This limit is the ultimate test for our understanding of matter under the most extreme conditions imaginable, but recently, astronomers have spotted neutron stars that are flirting with this cosmic speed limit. Observations of massive binary systems, where one neutron star siphons material from a companion, have revealed objects pushing dangerously close to that theoretical ceiling. Some measurements suggest neutron stars may exist with masses around 2.3 or even 2.4 times that of the Sun. Each new, heavier discovery sends a tremor through the world of theoretical physics. If these stars are real and they are not collapsing, then our equation of state for ultra-dense matter is fundamentally wrong. This equation is our best guess at how matter behaves when it is squeezed into such an insane density. Is it a soup of free-floating quarks? Does it form exotic states of matter like a superfluid or a solid crystalline core? The precise nature of this matter dictates how much pressure it can generate to fight gravity. A soft equation of state means the matter is more compressible, leading to a lower maximum mass and smaller stars. A stiff equation of state allows for more massive and larger stars. The existence of these incredibly heavy neutron stars points to an unexpectedly stiff equation of state, one that involves forces and interactions we have not yet accounted for in our laboratories. We are being forced to rewrite the physics of the impossible, all by observing the faint, persistent light of a star that by all rights should have already disappeared from our universe. This final cosmic defiance offers no gentle fade, but a violent, spectacular end. Phantom energy is the ultimate escalation of dark energy, a hypothetical substance so potent it would make the universe's current acceleration seem like a gentle stroll. Imagine dark energy as a constant force, its density unchanging as space expands. Phantom energy is far more terrifying. Its density would actually increase over time, growing stronger and more repulsive as the universe gets bigger and emptier. This creates a runaway feedback loop of destruction. As space expands, phantom energy strengthens, causing space to expand faster, which makes phantom energy stronger still. The end result of this catastrophic cycle is known as the Big Rip. First, the phantom energy's grip would overcome the gravitational glue holding galaxy clusters together. These vast cities of stars would be flung apart into the lonely dark. Next, the force would invade individual galaxies. The Milky Way itself would be shredded, its billions of stars scattered like dust in a hurricane. Then it would turn on solar systems. The sun's gravity would be no match for this cosmic tide, and planets would be torn from their orbits. In the final, gruesome moments, the force would target individual structures. Stars and planets would be ripped apart, their atoms unable to withstand the overwhelming pressure. Molecules, atomic nuclei, and even space-time itself would be stretched and fractured beyond recognition. The very fabric of reality would be torn to pieces, leaving behind a cold, featureless, and utterly lifeless void where not even the concept of here and there could exist. This ultimate dissolution would defy every principle of a stable, predictable cosmos, proving that the universe's final law might not be one of preservation, but of absolute, unforgiving annihilation. From the ghostly tug on distant probes to the ultimate threat of a phantom-fueled Big Rip, we have journeyed through 30 cosmic enigmas where the universe itself seems to break its own rules. Each mystery, from the wow signal's fleeting hello to the silent dance of dark matter, is not a sign of science failing, but a beacon guiding us toward a deeper truth. These apparent defiances are the universe's way of teaching us that our current knowledge is merely a prologue to a much grander story. They are the cracks through which new light shines, pushing humanity to forge new theories and question our most fundamental assumptions about reality. So the next time you find yourself under a clear night sky, remember that the quiet darkness above is filled with more wonder and mystery than we can possibly conceive. Let that feeling of awe fuel your own curiosity. Tell us which of these cosmic puzzles keeps you wondering, which single mystery makes you look up at the stars and question everything you thought you knew. Share your thoughts below and never stop exploring the beautiful, rule-breaking strangeness of our cosmos.